Okay, uh, right, let's start the class. So we have been dealing with so far with phase diagram, and actually this is the something very closely related with the last lesson. Uh, we are going to have a look on the iron carbon system. Actually, when we say the system means we refer to the phase diagram itself, right? So why do we have to look at the iron carbon system specifically? Because iron is widely used, the most used materials. So you can find almost all places we use the iron as the material. So it is really important to understand this system to have a better understanding on the whether it is mechanical structure and maybe the structural integrity, right? So So in this lesson, we are going to focus on how we can identify the major phases on the ferrum, the iron and carbon phase diagram, and we explain their characteristic. And also, we want to have a look on the hypoeutectoid, hypereutectoid, proeutectoid, and perlite. I guess this one is the first time you hear this one, perlite. For the other, I think in the last lesson we have a bit maybe define on these terms. I'm not sure whether you remember or not, but we will still have some refresh uh, refreshing session to again recall our this term, what it means. And we also want to identify the proeutectoid phase, and we want to know the fraction, and we want to also calculate for the proeutectoid and the uh, the phase, the perlite after the eutectoid line. So anyway, we go by one line by line. So this is the introduction. We are going to actually have a look on this iron. So the iron actually in pure form, uh, well, it has good characteristic, good electrical and thermal conductivity. It also easy to magnetize, but the problem is with pure iron, it is very soft and readily oxidized. So to solve this, what we do is alloying. Alloying. I guess you guys are already familiar with alloying. So what we do is we add some other element, and in this case, because we are focusing on the iron carbon, and because the carbon is the most well, when we say iron, we always uh, relate it with steel. You know, if you don't study about the material science, maybe we cannot differentiate what is iron, what is steel, what is iron, what is steel. So we don't, layman, they don't really understand the difference between these two words. But for you guys, future engineers and scientists, it is very important for you guys to be able to distinguish these two things. Okay, iron is the Fe, yeah? the Fe. This is the iron. And if you introduce some amount of carbon inside, then it becomes steel. And actually for steel, let's see. Okay, before we go on into understanding the steel, okay, let's have a look on the pure iron itself first. So this is a diagram telling us the phase of this iron. Actually, it has three electrodes. Okay, from liquid, when the temperature, okay, let's say atmospheric condition. So this is for atmospheric is around 1 bar. So this line, atmospheric condition. So at 1538 degree and above, the pure iron, we are talking about the pure iron. Pure iron exists in form of liquid, right? So when it reaches 1538 during the cooling, so when it reaches 1538 degree, the solidification starts, and we will have at first the delta ion, which is the BCC, which has the BCC crystal structure. And as the solidification, as the cooling, it's already solidified. As the cooling continues, the solid of delta become the gamma ion, and gamma is a different phase. It has the structure of FCC, and eventually, when it exceeds 910 during the cooling, so we will have again the BCC structure of alpha, right? So this is the basic information for us before we take a deeper look on the steel. Okay, this is the iron. Okay, and during the solidification, yeah, this is actually what I have mentioned just now. So when it exceeds this one, it become the BCC, and then when it, you know, cool further, become the FCC, and again BCC of alpha. So this is how it looks for the pure iron. Okay, so this is the microstructure of the pure iron. Okay, without any addition. Uh, oops. Right. And okay, this is what we are going to focus on. Actually, for the steel, okay. Well, steel is defined, okay, when you add up to 2%. This is the range of the steel, okay. Uh, if more than that, it become the cast iron. If more than 2 become the cast iron, or more precisely 2.06. Okay, so we are going to have a look on this yellow area, which is the steel. Okay, so when we give when we explain on what is steel, when we differentiate, we would want to at first say, okay, iron is the pure Fe. Iron is the pure metal, right? So when you add some carbon, it will become steel. But how much? It is must be below 2%. That is steel, right? And well, this is the solidification of steel. All right, so you have these what you call as the carbon atom, which dissolve or soluble in the iron crystal structure. So the iron is the host. The iron is the host, and we have this alloying element of carbon, right? So it get in between. Institutionally, it spread uh, throughout the iron crystal structure, right? So uh, okay, so we have that up to 2% of carbon still behave during emission like solid solution. Carbon atom completely soluble in Fe crystal structure. So this is the solute. This is the solvent. So they become solid solution. Right. So austenite is the FCC lattice structure of gamma ion with carbon atom within the interstitial space. So what is austenite? What is austenite? We have a look already on the just now this one. So this gamma area. Okay, this is gamma area. This is gamma ion. So when it is FCC, okay, FCC. But when we introduce the carbon, so the carbon gets uh, is in between those atoms, and we call this phase as austenite. Okay, FCC gamma ion with carbon. That is austenite. Okay, that is austenite. So okay, cool enough. So we want to when the solidification it continues. Okay, when it continues. So what happened actually the from the austenite phase you know austenite is in FCC, yeah, FCC, and when it goes below the 770, okay, so what happened, the FCC start to change into BCC, okay, and this BCC is called BCC. This alpha ferrum is called the ferrite. Okay, it's called the ferrite, and okay, this BCC is this iron. Particular this iron is called the ferrite. Ferrite. Okay, and during this transformation, austenite is solid. Okay, austenite is solid. Ferrite also solid. Okay, ferrite also is solid. So what happened actually? We have to focus on the solubility of the carbon in the ferrite. So okay, the max solubility of carbon atom in PCC is only 0.02, means it's very little, very only little carbon can be occupied or can be accommodated uh, in the uh, BCC crystal structure. Okay, the BCC or the ferrite can only accommodate very little, and this is at 7 to 3, and it further become very less soluble uh, when it reached the room temperature, and it's recorded as 0.01%. So it's very, very, very little carbon that can be dissolved in the BCC crystal structure, or more precisely in uh, the ferrite, in the ferrite. So this actually caused during the transformation, during the transformation, the carbon pressed out. It is pressed out, okay, from the lattice. So you can see from this one, from this austenite, where carbon is, uh, I could say it has higher solubility and better, better, more space, more space to get into the crystal structure. When it becomes BCC, so it is squeezed out. It's squeezed out. Okay, something like this. It's squeezed out. All right, and okay, and also for the in the austenite itself, even okay, during the solidification, of course, the cooling take place, and lower temperature cause this carbon atom to be more less soluble, and this cause lattice distortion because it get shrink, so it's pressed, and the distortion become higher. Okay, so okay, yeah, for this actually it has two modes. Okay, for steel, which is 2% and below. Okay, 2% and below means 2%. Let's see, so that we have clear view. So means this is little, sikit lah carbon dia. This one is more. Okay, this one is more. So when we talk about this amount of carbon, because it is so little, so when it is squeezed out, okay, it grabs some of the iron together, and they form this Fe3C, which is uh, the carbide, iron carbide compound, this one. Okay, so yes, this one from austenite, okay, it changed into the ferrite. Okay, austenite changed to ferrite, and this carbon, it has to go out because of low solubility. Okay, this has higher C solubility. Okay, and this is lower carbon solubility. Okay, so you can imagine, uh, at first when you have more money, you have bigger house, so you can accommodate maybe 10 people. But sometimes when COVID come, then you have no money, you rent a smaller house, then what happened, some of them have to go out. So most probably the one which is freeloader lah, the carbon, it's not the the iron itself. The freeloader have to go out lah. Okay, so that is how it works. Yeah? So when the transformation from austenite to ferrite, the solubility is greatly decreased, and this causes the carbon to be squeezed out of the of the crystal structure, and the squeeze outs in form of what? In form of what we call cementite, or the this is the name lah. This is the name, and it is iron carbide lah. Yeah? The compound is one of the iron and carbon, so it's iron carbide, and the name is the cementite. This is ferrite and cementite. This is for steel, for 2% and below. But if in case of high content of carbon, the carbon they can get together and they will form the graphite. This is for high content, not the steel, right? So, and steel we can actually classify into three: Eutectoid steel, hypo-eutectide, hyper-eutectoid. Okay, hyper-eutectoid. So I guess we have already have some experience on this term, hyper-eutectoid, hypo-eutectoid. Okay. So at first, what is eutectoid? Eutectoid is eutectic liquid to two solid. Okay, eutectoid, one solid to two solid. Okay, so we have austenite. Austenite given by delta. I forgot. Sorry, the gamma, alpha dengan cementite. Okay. Okay, ni ada kat sini. So gamma, alright, into alpha plus cementite. So two phase lah, one phase into two phase. This is eutectoid. Okay, eutectoid. This exact, this one lah, the exact from one into two. Okay, if it a little bit diverted, it has this in between this there is some intermediate process. So you have the gamma, and at first you have gamma and alpha, and then after that become gamma, alpha and cementite. So what happened? Okay, first let's take a look on the eutectoid. So okay, you have this is weight percent. So you have the iron, pure iron, and then you bring 0.77 weight percent of carbon. Okay, and you mix them, and then you heat up, and you will at first, of course, you will have the liquid, and then it solidify into austenite. So this is already solid. So because austenite, you cool it off little by little, and at 727 degree. This 100% austenite, it change into the combination of ferrite and cementite. Cementite is the iron carbon lah. Okay. The name lah. Okay. And this lamellar structured ferrite and cementite, this lamellar structure is what we call pearlite. So this is very important term. So when people say pearlite, we already have this this image of lamellar structure between ferrite, which is the alpha ferrum, the ferrite, and cementite. We have this image. This image. When you say perlite, this is the thing. Okay. At the eutectoid point, okay, it become this perlite crystal structure. And how does this eutectoid steel looks like? Okay, this is the picture or the image. You can see that there is lamellar structure throughout the materials. Okay, so ferrite and cementite. What is ferrite? Ferrite is alpha iron. Cementite is iron carbide. Right. Just the name lah, just the name. Okay. Ferrite, cementite. And these two, this connectivity, this lamellar structure of these two, it forms what we call, in total, we call it perlite. We call it perlite. Okay. So, boleh faham tak setakat tu? Do you guys understand what I'm explaining now? Faham tak setakat tu? Setakat sekarang?
Boleh sir.
Sikit-sikit. Okay, saya terang dalam sikit lah, saya terang dalam bahasa Melayu sikit. Takut tak faham. So macam ni lah. Dia kita iron tu adalah pure besi lah, pure ferrum. Tapi kalau kita campur dengan carbon sikit untuk kuatkan dia jadi kuat apa yang kita cakap sebagai steel. Okay, itu point nombor 1. Okay, point nombor 2, bila kita meltkan benda ni dan kita solidify, kita bagi dia cool slowly, apa jadi adalah benda ni, substance ni dia akan bertukar jadi solid, yang mana solid ni dalam crystal structure tu dalam keadaan FCC, phase center cubic. Okay, dan phase center cubic ni dia boleh accumulate, dia boleh simpan, dia boleh cover, dia boleh contain a higher amount of carbon. Dia boleh contain higher amount of carbon. So carbon ni dia tak nampak terkeluar tau. Dia nampak satu phase je, duduk dalam. Okay, tapi bila kita sejukkan dia lagi, bila kita cool it off a little bit more, what happen? Dia tukar crystal structure dia daripada FCC jadi BCC. So BCC ni satu crystal structure yang dia kurang boleh accommodate carbon sebab dia punya structure dia kecil. Dia lebih kata padat. So apa jadi? Solubility carbon akan berkurang. Okay, solubility carbon akan berkurang. Dan ini menyebabkan carbon tu terkeluar daripada sebab dia awal-awal FCC, dia tukar jadi BCC, carbon terpaksa keluar. Dan carbon ni dia keluar dalam keadaan orang panggil bukan dia carbon semata-mata, dia juga ambil sikit iron ni, dia jadi orang kata ferrum carbide. Dia jadi campuran antara compound ferrum iron ni dengan dia carbon ni dia bawa sekali dan dia bentuk suatu phase yang baru. Phase ni iron carbide ataupun kita panggil dia cementite. Okay, and yang tinggal adalah iron sajalah. And iron ni dalam keadaan BCC, dan iron ni kita panggil dia ferrite. So very simple actually. Okay. Alright, so we continue. right? Oh, okay. And then and then if we have the exact composition of 0.77 percent, we will have this line at eutectoid lah. And this is what we call eutectoid steel. Okay, this is what we call eutectoid steel. But okay, and this is how it looks like lah. It looks like the carbon that been squeezed out, and it brings along some iron, forming the cementite, okay, and the remaining ferrite. They form this lamella because it happens very fast. Okay, they don't have time to come together. So because it happen fast, so eutectoid, because eutectoid it happen very fast. So from one solid directly to this two phases, so it become the lamella. So when we divert a little bit the composition, say we decrease the carbon, okay, we decrease the carbon, so this line will be shifted to the left because carbon is less. So when carbon is less, this line, we don't call it this steel, we don't call it eutectoid steel anymore, but rather we call it hypoeutectoid. Okay, so hypoeutectoid, you have this transition phase from this austenites, the gamma phase, into the gamma plus alpha. Okay. Gamma, it becomes gamma plus alpha first. Okay, and then after that, we the alpha, the gamma. Okay, gamma become partially. Okay, I can say this is partially become alpha first lah. Okay, we still have the gamma, but some of them already become uh, the alpha. Okay, this is the how it looks like lah. Okay, this is how it looks like. So we have this austenite, the orange. Okay, and at this phase, partially some of the austenite they form ferrite. They form ferrite. Ferrite BCC lah. Okay, and the remaining austenite, when it reach this line, the remaining, same like eutectoid, the remaining it change directly into those two cementite and ferrite. There's those two iron carbide and iron itself. Okay, they form this lamella structure, and those ferrite which form before the eutectoid line, what we will call them as pro-eutectoid, or maybe we can also call primary, pro-eutectoid, right? And yeah, this is hypoeutectoid. Okay, this, I think this one what I was telling just now lah. Okay, this is the continuation, and the remaining FT will have eutectoid composition, and it will transform to perlite. So actually what happened, to be precise, so okay, so when you, this one you have to work out your mind a little bit lah. Okay, okay, when we say we have a smaller amount of carbon, means higher amount of ferrum, which means we have higher amount of ferrum. Okay, eutectoid is fixed. Okay, eutectoid is fixed. Eutectoid is fixed. All right. So when we have higher amount, lower amount of carbon, it means indirectly we say that we have more iron. Okay, so iron at first we dispose first. We let it out of the system first, out of the austenite first. So when adequate iron has been kicked out, okay, so we left those austenite with a lower amount of ferrite. So when it reaches the eutectoid, means it reached this one 0.77. The remaining austenite have this composition. That is why it become this pearlite. Okay, it become this stripe. So indirectly lah, if you don't want to remember only like then just to deepen your understanding, actually that is what happened lah. So okay, how this is how it looks like. Okay, there is a Eutectoid steel, and we have a cementite protruded from the surface. Okay, so you can see clearly there are two phases. One is the bright one, and then this darker one. And okay, let's see. Okay, then we go to the hyper-eutectic. Hyper-eutectic. So hyper-eutectic means we have the amount of carbon is more. Okay, the amount of carbon is more than the eutectoid. Eutectoid is fixed, like I said. Eutectoid is fixed, never change. Eutectoid is fixed. Okay. So we have more carbon. Okay. So what happened? At first, from here, from 100% austenite, we cool it off, and then we reach this phase of the austenite and the cementite, or the carbon iron carbide, or the iron carbide. Okay, so let's say what happened actually same with this hyper-eutectoid, the cementite, it some amount of austenite, it transform into cementite. And when it reaches this line, it means that the remaining austenite have the eutectoid composition. And with eutectoid composition, we have this lamellar structure. And this is what happened. And you can see that there is a formation of cementite in blue color. So cementite first, and pro-eutectoid. Okay, pro-eutectoid ferrite you have here in yellow for the hypo-eutectoid. Yes, so this is how the hyper-eutectoid looks like, and we can see that there is a pro-eutectoid cementite residing at the grain boundary. This is the grain boundary. So this is the cementite. This is the cementite. Okay. Okay. So when we talk about the structure, we want to have a bit relation with the strength or the mechanical properties. Okay, you see that when we have 100% perlite, 100% perlite, okay, when we have this 100% perlite, the strength is at its highest. And this is because this alternating microstructure, actually you can think of it like the hindrance, like we discussed about the grain boundary. we say that the grain boundary, if big, big means the interface is little, but if it is small, very small grain boundary, it has more hindrance for the dislocation to move. So likewise, the same, when we have those lamellar structure, we have higher amount of interfaces, and with those dislocation, it cannot, freely move, and then that is why it is more, uh, it has higher strength. Okay, and yes, this is some calculation. I think we are already getting used to this, what we call as lever rule. So using the lever rule, we will know how much is the ferrite, how much is the cementite. So you want to evaluate that, you have to say this phase lah at the bottom. So you see that when we use the lever rule, you need to refer to the phase diagram. Okay, this one. Okay, so you look. This is the area that we are talking about. The area we are talking about. All this area. So when you look to the left, you have the ferrite. You look to the right. Okay, there is no phase until here. This is 6%. 6%. This is intermetallic compound. Okay, this line actually is the intermetallic compound. It's as if we cut those intermetallic compound line, like the one that we discussed last week. Okay, so this is very small. You can see that Fe3C. This is where you look to the left, there is ferrite. You look to the left, to the right, there is Fe3C, the carbide, the cementite, iron carbide. So you use the lever rule. You check. This is actually 6.67. Okay, so you use the lever rule. What you have to do is you have to get those from zero to the line of the cementite is 6.67. Okay, so if we want to know about the ferrite, how much is the ferrite? Okay, from this line, we want to know the ferrite. We take the other way around here. From here to the end of the line is 6.67 minus 0.5, and the remaining here we can calculate the phase fraction of the cementite. Okay, so this is 0. Cementite is right here, so from ferrite is here, so we take the other way around. This one, take this one, take this one. So we have this one, and then this is the calculation that we have for those 0.5, for the 0.5%. And if we want to calculate, or we want to have this, we want to know how much is the pro-eutectoid, or in this case pro-ferrite, because it's hypo-eutectoid, so it's pro-ferrite. How much is the pro-ferrite? We use the lever rule. It's the same. From here, instead of going, we take this, instead of looking at the carbide, or the iron carbide or the cementite, we take it here. Okay, and because this is where the line, and then this is the eutectoid point. So whatever occurs here, okay, here is what we can actually use. This whole amount is the length, okay, 0.77. Okay, from here to here is 0.77. But to get the perlite, we have, because perlite is this side, you know, this is the eutectoid line. It should have perlite here. So perlite, we don't take this one, we take the other way around here. And then for the pro-eutectoid, you use this one, the remaining, which become the ferrite. So we calculate, we know how much from the whole ferrite. From the whole, we know that there is how much is the pro-ferrite, how much is the perlite. So the summary, uh, okay, so I think the time has been very tight. So just in short, you can read the summary. We have yeah, this iron carbon alloy. We can produce this. There is a eutectoid composition, and this is eutectoid. It produced perlite, which is the alternating layers of ferrite and cementite. And for below, for below the eutectoid point, we have hypoeutectoid, and these have the pro-eutectoid ferrite in the beginning of the solidification, and for the on the other way we have the hypereutectoid. So in the beginning it caused the austenite to change to the cementite little bit, and this cementite, it caused, after the cementite is formed, then it become again the lamellar structure of eutectoid. And then the mass fraction, just we mentioned just now, we can use the lever rule. Okay, so that is all for today. I hope you understand the iron carbon for this very short period of time. So if you have question, you can always reach me by the WhatsApp. So thank you for today. Sorry for taking 2 minutes of your time. So see you guys on day after tomorrow. Yep. Okay, bye.
Thank you, sir.
Bye.
Okay, Doctor.
Thank you.
Yeah, the
Thank you, Doctor.
Okay.